Let's look at the nature of ionic and covalent bonding as seen through the lens of quantum mechanics. Now, let's interpret the investigation that you did when you melted and dissolved a number of compounds, or tried to melt and dissolve chemical compounds. The ionic compounds, like sodium chloride, did not melt at the relatively low temperatures that you could get with a hot plate. They did break up in water, generally, and when they broke up in water, they formed ions that conduct electricity. The covalently bonded compounds, like sucrose, melted at low temperatures, melted rather readily, and some of them may have even evaporated. They sometimes dissolved and sometimes didn't, but they never conducted electricity. Except if you use benzoic acid, you may have seen a very tiny conductance. Let's look at the octet rule. The outer or valence electrons of a noble gas form an octet, that is, 8 electrons. That's a full s orbital and 3 full p orbitals, like 2s, 2, 2p6. Octets, even in molecules, are low energy. They're very stable electron configurations. Now in ions, of course, they are not only very stable, they're belonging to the ion itself. So sodium has lost an electron and has a S2P6 configuration because it's lost that outer shell electron, and the chloride, of course, has gained an electron to give it, in that case, a 3s2 3p6 configuration. All of those are very low energy. So atoms tend towards an 8 electron outer shell, an octet. Nonmetals do it by adding electrons, metals by losing electrons. And when they form those ions, they form charged particles which have a very, very high attraction for each other, and therefore they don't melt very easily. You have to apply a huge amount of heat in order to get them to separate from each other. Ionic bonding, metal atom loses the electron and becomes a positive ion. The nonmetal gains an electron and becomes a negative ion, and plus attracts minus. It's as simple as that. The bond is very, very strong. Therefore, the melting is very difficult. Now, water has enough energy to separate the sodium and the chloride, and we'll see later water is also a polar molecule, which gives it an advantage when it comes to dissolving these ionic compounds. The octet rule also governs covalent bonding. So, for instance, OF2, oxygen difluoride, looks like this. If you count electrons around each atom, here's the fluoride, here's the oxygen, here's the other fluorine, you can see there's 8 here and 8 here because they share. There's a sharing of these bonding pairs. Covalent means sharing. The fundamental reality is that 2 electrons are being shared in one bonding orbital. If 2 electrons have 1 electron, if 2 atoms have 1 electron, then each is going to need 1 electron to finish a bonding orbital. If their electronegativities are similar, neither of these atoms can take the other's electron, and therefore they share 2 electrons by overlapping, by adding the atomic orbitals together. The result is what we call a molecular orbital, or MO. The electron spins, of course, must be opposite for them to fit into the same orbital. So, look at hydrogen. We get overlapping 1s orbitals from 2 atoms to form the bonding orbital, or a molecular orbital. We can represent these by Lewis structures in the following way. We form the bond, and now we have the bonding pair between the 2 hydrogen nuclei. Obviously, hydrogen is a linear molecule. There is no other way it can be. Here's a space-filling model that you can see. This is very easy to do with a graphics program. And you may also know that a bonding pair can be represented with a line or a stick. And that's another way to show a chemical covalent bond. So the space-filling model, the stick, or the double dot all represent two electrons holding the atom together in a covalent bond. Now the first bond between two atoms, the one right between the two nuclei, is called a sigma bond. This is going to be important when you get to AP chemistry. We continue our interpretation of the experiment. Covalently bonded compounds form individual molecules. We call these molecular compounds. These molecules are discrete units. They don't attract each other very strongly. They're sufficient within themselves. They're not charged. They're not ions. So they don't attract anything else by simple plus to minus attraction. The attractive force that they do have for each other is very weak. We'll learn more about that in AP chemistry, what we call dispersion forces. And heat very easily breaks the attraction between these molecules. So therefore they melt at low temperatures. And that's why the sucrose and the other molecular compounds that you used were able to be melted even on a hot plate. So in the solid phase, these sucrose molecules are in a lattice with weak attraction. And when we heat them, that shakes the lattice apart, but it does not pull the molecules apart. Each molecule remains in its original configuration. Now, if you heat it enough, you can break these up. And if you heated your sucrose a lot, you probably saw the water come off and black carbon residue on the aluminum foil. This is why, of course, sucrose and the other molecular compounds melted on the hot plate. Now, molecular compounds differ from the ionic. Ionic compounds form networks of ions that are electrically neutral. But each positive ion, each cation, is not associated with a particular anion. They don't hang together when at high temperatures they melt. But molecular compounds form discrete units of two or more atoms. These stay bonded to each other even when the compound melts or boils. So if this is a, say, oxygen molecule, even if it boils, these two atoms continue to be stuck to each other. Sharing of electrons occurs if the atoms involved acquire the electron configurations of noble gases, generally octets, when they share. Typically, covalency occurs between atoms in groups 4A, 5A, 6A, and 7A. You probably know these as 14, 15, 16, and 17 of the periodic table. And that's the reason that halogens, oxygen, and nitrogen gases, the elements, are diatomic. Their overlapping orbitals permit them to have octets together. For instance, oxygen, as you can see, we have the 6 electrons in the valence shell here, and the other one 6 electrons, and we can see now 2 overlapping orbitals between the oxygens. Now you need to memorize the diatomic elements. Very important. Hydrogen, nitrogen, oxygen, fluorine, chlorine, bromine, and iodine all come in packages of 2. They overlap their orbitals because each of them has incomplete octets. Now there's a test question that many get wrong. What is the mass of 4 moles of oxygen gas? Typically, people will say 4 times 16. But oxygen is diatomic. It comes in packages of 2. So to get this right, remember oxygen is O2, just as you learned in biology. It's not a single atom. So 1 mole of oxygen gas is 16 times 2 moles of atoms times 16, or 32 grams per mole of oxygen gas. And 4 moles would be 128 grams of oxygen gas. Here are the diatomic gases in their Lewis diagram and stick model. You'll notice fluorine has 1 bonding orbital, oxygen has 2, and nitrogen has 3. Because nitrogen has 5 valence electrons, oxygen has 6, and fluorine has 7. Now, you'll recall that molecular compounds form discrete molecules with covalent bonding. But if you look at water, water has 2 bonded pairs, 1, 2, and 2 unbonded pairs. Now this is important because the electrons still have their negative charges. So water is not linear. It's got its unbonded electrons on one side and its hydrogens bonded on the other side. As you can see in the space-filling model, it has these offset. Nitrogen trihydride, or ammonia, has a similar situation. Ammonia has 3 bonded pairs of electrons, 1, 2, 3, and 1 unbonded pair, which in the space-filling model would show up right up here on the top of the molecule. So ammonia also is kind of lopsided. We call these polar molecules. Lopsided molecules are polar molecules. It's like they have a north and south pole, but instead of magnetic, the poles are electrostatic. Plus and minus. Water, ammonia are 2 of our important polar molecules. Hydrogen chloride is a diatomic molecule with a single covalent bond. Why don't you draw the electron dot structure for HCl and ask, is it polar? You can turn off the video and come back to it for the answer. There's your HCl in the Lewis structure, and here is a space-filling model hydrogen, very small compared to the chlorine. It's linear, but the chlorine is a lot more electronegative than the hydrogen, so the electrons spend a lot more time around the chloride than around the hydrogen. Here's the mosquito graph of the probability, and you see the density of the electrons around the chlorine is much higher than around the hydrogen. So, practice the electron dot structure for hydrogen peroxide and ask if it's polar. It has 1 more oxygen atom than a water molecule, suggesting that 1 oxygen is bonded to the other and each to a hydrogen. And so, it looks like it's polar because you've got a negative end and the hydrogen positive end. The electrons are on one side, the hydrogens are on the other. If you have a double or triple bond, as you've seen before, the second and third bonds are not directly between the atoms. They're above and below the atomic plane. These second bonds or third bonds are called pi bonds, and they are not directly between the 2 nuclei as the sigma bond is. So, a review. Ionic bonding is simpler than covalent. In the oxidation, the metal has lost an electron, and the ion that results has a positive charge. The nonmetal has gained electrons and gets a negative charge, and they attract each other with a very strong electrostatic charge. Here's a picture. Positively charged ion attracts the negatively charged ion strongly, and the melting points are therefore very, very high. The bonds between these ions are very, very strong. So ionic compounds melt at a very high temperature.